Hello, welcome to Basics of Finite Element Part 2. This is the second week of this course, and in the last week we had reviewed a good number of topics which were covered in Basics of FEA Part 1, which was offered in the first part of this year, that is between January and March of 2016. So, what we are going to do today is we are going to look at errors, because every finite element solution is an inexact solution. The exact solution, so there is a difference between the exact solution and then the inexact solution, and the difference is the error. So, what we are going to do is we are going to look at different types of errors, and then we are also going to develop some metrics or measures as to how to quantify that error. So, that is another thing we will be looking at. And the third thing we will be looking at is convergence, that as you keep on making your finite element model better and better, your solution should approach the theoretical solution in a more close way. So, it should become closer to the exact solution. So, that is another aspect we are going to look at, that is convergence. So, that is the scope of this week's lectures, and specifically today we will be looking at errors, what are the sources of errors, and if we have time probably we will also cover how can we measure errors in an objective way. So, this is going to be our theme for today. Now, first we will look at different sources of errors. Different sources of errors. So, suppose we have a differential equation, second order differential equation, and let us say this differential equation is d by dx a du over dx is equal to f. Okay. So, that is my differential equation, and what this differential equation represents, one of the things which it can represent is that if you have a bar and you are pulling the bar like this, and if I am interested in finding out the displacement of this point u, then an A here is equal to Young's modulus of the material and cross section of the material at a particular cross section. So, this is the governing second order differential equation, and if we are able to solve this equation, we can get the solution for this bar problem. And the first step we said was that if we have to do finite element analysis, we have to discretize this bar into several elements. So, let us say this is element 1, this is element 2, this is element 3, this is element 4. So, in a simple way I can redraw this. So, this is element 1, 2, 3 and 4. So, these are the 4 elements. Okay. So, this is step 1, is discretize the domain. So, in this case we have discretized the entire bar, this is my bar, into 4 different elements, element number 1, element number 2, element number 3 and element 4. Then the second step which we discussed in the last week was, once we have discretized the domain, Then the second step is that we assume a function which represents variation of ux over each element. Okay. So, we can assume, so for instance, for suppose, so we can make some, so this is where we have to assume something, we have to assume a function. This is an important thing, we have to assume a function. Okay. So, one assumption could be that for the eth element, u of x for eth element could be sum of uj psi j, and this is eth element, so I am having superscript e. Actually, in past we have been doing like this. So, here these uj's are unknowns and this is a known function. Now, I can make several types of choices for psi j. Psi j can be linear function, it can be linear in x. Okay. If it is linear in x, then it will have a form of something like what, a plus bx form. It can be, psi j can also be quadratic, it can be cubic. So, if it is quadratic, it will be something like a plus bx plus cx square. If it is cubic, then this function will be a plus bx plus cx square plus dx cube. So, which type of psi j we choose, it depends on our assumption, and based on our assumption, it is the nature of this assumption, it introduces an error into the solution. So, that is why. So, this is the first error, first type of error which gets introduced into the solution. So, because of this assumption, so because of the choice of polynomial function representing u of e for u on eth element, an error is introduced. And this type of error is called approximation error. Okay. So, this is the first type of error which is there in our finite element solution, and the amount of this error is directly dependent on what type of function we choose as the approximation or the interpolation function. So, that is why, because it depends on the type of approximation function, that is why it is called approximation error. Okay. So, it is important to understand this. If we go to higher order polynomials, this approximation error becomes less. If we use lower order polynomials, the approximation error is more, and so on and so forth. Then in step 3, what do? We calculate weighted residual, we take the residue error on the equation or residue in the equation, multiplied by weight function and integrate it over the domain. So, we get element level equations, and then step 4 is assembly and step 5 is what? Application of boundary conditions, and step 6 is solving the equations. So, in all these steps, step 4, 5 and 6, we are not making any assumptions, right. Here we made an assumption in step 2, but here we are not making any assumptions. So, there is no approximation error which goes into step 4, step 5, step 6 and so on and so forth. But a different type of error is introduced in these steps. So, in step 3, step 4, step 5, step 6, all we are doing is we are doing a lot of calculations. So, the error, how accurate our calculations are, how many number of decimal places we are calculating our results up to, that is the related to the amount of error. Okay. So, in these steps we introduce finite arithmetic error. This is one thing, finite arithmetic error. For instance, if we are dividing 10 by 3 in computer, it could be 3, or it could be 3.3, or it could be 3.33, or it could be 3.3333, and so on and so forth. So, depending on how accurate we compute, we do our computations, our results will be proportionally accurate. Another source of error is when we do the integration. When we do the integration, this is something we will learn maybe next week, then we integrate it using a method called Gaussian quadrature method. So, depending on which type of how many quadrature points we pick are integrals, because in step 3 we have to calculate integrals of weighted residues over the domain. So, how accurate we are in computing the integrals. So, that error is quadrature error. And this depends on accuracy of calculating integrals. But both of these errors, finite arithmetic error and quadrature error, they are related to the numerical procedure which we are going to follow. So, this is the second source of error. So, the first source of error was approximation error. First source was approximation error. The second source of error is this thing, computational error, which can be of two types, finite arithmetic error and quadrature error. Okay. So, this is the second source of error. So, principally these are the two broad types of errors which are there in picture when we handle one dimensional problems such as this. So, this is a 1D problem. Okay. So, in one dimensional problems, it does not matter whether it is a second order equation or fourth order equation. In one dimensional problems, we have primarily two types of errors. First one is approximation error, the other one is computational error, which can be of two types, finite arithmetic and quadrature. But in 2-dimension and 3-dimensional problems, we have a third type of error which comes into picture. So, let us see this. So, in 2-dimensional and 3-dimensional problems, we still have approximation error and we still have computational errors like finite arithmetic and quadrature errors. These two errors are there in 2D and 3D problems also, but we have an additional error in 2D and 3D problems. So, in 2D and 3D problems, we have an additional source of error. And what is that source? So, we will illustrate it by example. So, suppose I have a circle a disk, let us say it is a disk, and on this disk I am fixing one end and I am putting a force on this end. So, this is a metallic disk, I am putting force on one end and at the other end I am fixing it, and I am interested in finding u and v. U is the displacement in x direction and v is the so this is my coordinate system x and y. So, at some arbitrary point p, I am interested in finding the displacement in x direction, which is u, and displacement in y direction, which is v. So, I can solve this using analytical approaches or by finite element method. But when I do finite element analysis, what is the first step? The first step is that we discretize the domain, does not change whether it is 1D or 2D or 3D problem, the approach remains same. But in 1D problem, there is no error introduced when we are discretizing the domain. When we discretize the domain in 2D problem, what do? We essentially break this circle into either triangles or rectangles or some quadrilaterals, something like that. So, if I am breaking it up into triangles, so this is very coarse mesh, then these are the boundaries of triangles. Right. And what we have is this extra stuff, this green area. So, the green area is not covered by these triangles. This remains outside the triangles. So, in our finite element model, we are not able to capture the geometry accurately if I am using triangular elements. Okay, if I am using triangular elements. So, this is a third source of error which was not present in 1D problems. In 1D problem, we have a straight line and that line is broken into smaller lines. So, there is no problem of geometric approximation. So, here this is the third type of error and this is called, so this third type of error is called computational domain error. Okay. This is the third type of problem. It is computational domain error. What it means is that I am able to capture the domain computationally in an approximate way, not in an exact way. So, this is the third source of error, and this error, how can we reduce it? If I reduce the element size, right? If I reduce the element size, so suppose these are three things. Suppose I have to represent this rectangle, this circle by rectangular elements. So, here element size is 1. Now, another way I can do it is, I can have smaller elements So, this is one approximation, right. So, here in the first case, all this was not included in the domain. Here the domain error, computational domain error has become smaller. This is the hashed area which is not included. And if I reduce the element size further, this domain error, computational domain error will go down further. So, the computational domain error, it decreases. with reduction in element size. The other way you can reduce this error is that you don't not only restrict, you expand the choice of your elements. So, right now we have just talked that our elements are having straight edges, right. So, it could be a trapezoid or a quadrilateral, things like that. But if I am smart, maybe I can also devise elements where one edge is curved, where one edge is curved. So, then if I have curved edges, then I can very easily reduce this error rapidly. So, if I have a 3 edge element where 2 edges are straight and the third edge is curved, then I can fit this type of element like this, and it will be much more accurate. So, I can reduce computational domain error in two ways. One is by reducing the element size, and second is by having elements which have curved edges. This completes the description of different types of errors which are there in our finite element model. So, overall what we have seen is that in one dimensional problems we have two types of errors which come into picture. The first error is approximation error, and the second error is computational error, right, related to computational procedures, mathematical errors, and those are could be related to quadrature error or finite element error. But in two dimensional and three dimensional problems, we have a second error which comes into third error which comes into picture, which is computational domain error. And the nature of this error lies in the fact that straight edged elements cannot accurately capture curved geometry. So, either to address this error or reduce this error, either I reduce the size of the elements or I introduce some fancier elements where at least one edge of the elements is curved in nature. So, this is the overview of different types of errors which are there in FEA, and we will continue the discussion in the next class. And specifically what we will cover in the next class is that how can we measure different types of errors. So, that is pretty much for today. Thank you very much and have a great day.